Okay. Now, to conclude today's lecture, we show you an example of computing integral. So, I is triple integral z square dx dy dz. What's omega? Omega is this domain x, y, z. 0 less than z less than h. H square r square x square plus y square less than z square. So to compute a concrete integral, you need to be able to draw the picture of the domain of integration. So we draw the picture first. This is analytic geometry. Okay. Firstly, we draw the coordinate axis. So this is x, this is y, this is z. And then for omega z, the range of z is 0 and h. So this is a plane equal h. And then the xy is bounded by this x square plus y square less than r square h square z square. So this is a cone. Okay. You take this as equality, then this is the surface, this is the cone, which vertex at the origin, and which the axis, the z-axis. And when z equal to h, this will cancel. Therefore, this is the projection is the a disk in xy plane, which is radius capital R. So this is the cone. Okay. The domain omega is bounded by the plane z equal to h, and the cone x square plus y square equal r square over h square multiply z square. So this is our omega. And the projection of this omega in xy plane is a disk of radius r. Okay, so this is the geometric analysis of our integrating domain. So how to compute this integral? The phi plus xy can be considered as h. That is the upper boundary of the domain. Upper boundary. And phi minus xy, that is the equation of the cone of the surface of the lower boundary. The lower boundary is here. Maybe I change the color. So this point is the surface. So this is square root of x square plus y square. Maybe I will erase this. Okay. HR square root of x square plus y square. Therefore, by the theorem we just proved, our I will equal the U is our disk in xy plane of radius r, and then the inside integral is definite integral from the lower boundary h r x squared plus y squared to the upper boundary, that is phi plus, that is h. Then our function fxyz is z squared, so this is z squared dz. So our triple integral is converted to computing a single variable integral first, and then compute the outer integral, that is a double integral. Okay, the dimension is reduced. Okay, so you can compute. The computation is quite tedious. I will not process, but I strongly suggest you to complete this computation after class. Okay, now I will give you another idea to compute the same integral. Quite very easy. Okay, so we denote by omega z. For a z here, for a given z, the corresponding omega z is the projection of the intersection of the domain which the plane z equal to z. Maybe z equal to z is quite strange. Maybe I will use another letter, t. Okay, so given t between 0 and h, our omega t is the intersection. It is the projection of the intersection of the plane z equal to t, which our domain. So this blue shadowed region is the intersection of the plane z equal to t, which our omega. Now you project it into the xy plane. This is a disk. This is the disk. This disk is our omega z. So analytically, omega z is a subset of xy plane. Therefore, the point has two coordinates, x and y, which satisfies the condition. So how to determine the radius of this projection, that is our omega z, is a disk. How to determine the radius of the disk? Here, the equation of the surface is equation of surface, the cone, is h squared over r squared x plus square plus y square equals z squared. Therefore, when z equal to t, this is x squared plus y squared equal to r squared, h squared, t squared. But this is the boundary of omega z, and the total omega z is less than equal to omega t. Okay, this omega t has volume. The area of omega t is pi trh squared. So our integral, our I, can be written by the t from 0 to h dt, then double integral of omega t. The function is fx is t squared, now is t squared, dx dy. So the inner integral, the integrand function does not depend on xy. It can be considered as a constant. Therefore, the value of the inside inner integral is t squared multiplied the volume of omega t. Therefore, this will be t squared. The volume of omega t is the volume of the disk, pi trh squared then dt. So this is the integral of a power function. It is very easy to compute. The result is 1/5 pi r square h cube. This is the final result. Okay, this result can be easily computed using the last integral in the definite integral in the right lower corner. Okay, so this method to compute is much simpler than our first method. Our first method is the first integral which back to z and then xy. Firstly, a single integral and then a double integral. But our second method, first a double integral and then a single integral. So you can compare. I ask you to complete the computation of the first method. First method, after you computing the inner definite integral here, you need to compute the double integral over the disk. So you have a long way to go, very complicated. But our second method, very quickly, our triple integral is converted to a single integral of a power function. You can compute the integral of the power function within a minute. Okay, so for this integral, the second method is better. But which method is better for your problem depends on the structure of the integrating domain. Also depends on the function you are going to integrate it. Okay, so our function here is z squared, does not depend on xy. So the inner integral in the second method is simply t squared multiplied the area of the omega t. Okay, so this makes the computation very easy. So I will stop here.